Welcome to Spaceverse, your portal to cosmic adventures. Before the Big Bang lies an enigmatic realm that has captured the curiosity of scientists and thinkers alike for decades, driving an ongoing quest for understanding the very origins of our universe. Recent breakthroughs in astrophysics and cosmology are shedding new light on this profound mystery, leading to unexpected insights that challenge conventional wisdom. Prominent physicists like Brian Cox argue that the commonly accepted idea of a hot, dense state prior to the Big Bang might be fundamentally flawed. Instead, they propose that the universe may have begun in a cold and empty state, undergoing a rapid expansion phase known as inflation. This inflationary epoch, which took place within the first moments of the universe's existence, fundamentally shaped the cosmos as we know it today. However, the process of inflation was not uniform across the entirety of the universe. It ceased in some regions while persisting in others. This discontinuity is what led to the event we refer to as the Big Bang in certain areas, while inflation continued elsewhere, creating a patchwork of cosmic development. This intriguing notion is part of a broader framework known as the inflationary multiverse theory, which posits that our universe is merely one of many existing in a vast cosmic landscape. The multiverse concept likens the universe to a fractal, where countless Big Bang events are happening across different regions of space and time, each giving rise to its own unique universe. Within this framework, our universe represents just a small segment of a far more intricate and expansive cosmic tapestry. To grasp the implications of inflation, it's essential to understand what this phenomenon entails and why it has perplexed scientists for so long. Inflation refers to the rapid expansion of space itself that occurred just after the Big Bang, driven by a peculiar form of energy, often referred to as inflaton energy. During this extraordinary phase, space expanded at an astonishing rate, smoothing out any initial irregularities and resulting in a flat and homogeneous universe. As inflation progressed, the energy responsible for this expansion eventually dissipated, leading to the release of heat and the creation of fundamental particles. This transition marks the genesis of the universe as we experience it, with the particles coming together to form the matter that constitutes everything around us today. The implications of these theories not only deepen our understanding of the cosmos, but also challenge our perceptions of reality itself, inviting us to reconsider our place within this vast and mysterious universe. Ultimately, the exploration of what existed before the Big Bang continues to inspire inquiry and debate, opening new avenues of investigation and inviting both scientists and enthusiasts to ponder the very nature of existence itself. We once believed that the Big Bang, this explosive release of energy, marked the beginning of everything. However, it is now understood to be just one chapter in the universe's history, prompting new inquiries. What existed before inflation? And why does the universe continue to expand? The universe is never truly empty. The concept of absolute nothingness doesn't apply in such a vast space. Even if we were to remove all the energy from the universe, it wouldn't be entirely devoid of content. New forms of energy are constantly generated as the universe expands. Even in the absence of particles, photons, and radiation, quantum fields, fundamental components of reality, persist. This is why space cannot be completely empty, and radiation is continually produced. True nothingness is impossible because these quantum fields ensure that there is always something present. So, could there have been nothing before the universe? Current understanding suggests that even in complete emptiness, space retains some energy. This zero-point energy represents the closest thing to nothingness we can conceive, yet it still signifies something, the minimum amount of energy that exists everywhere. The universe has evolved from its past to the present. It is in a constant state of flux. As space expands, it drives galaxies further apart and cools the universe overall. Initially, after the Big Bang, the universe was indeed in an extremely hot and dense state. As it expanded, it cooled down, allowing for the formation of subatomic particles and eventually atoms, leading to the creation of stars and galaxies. Redshift occurs because of the Doppler effect, where the wavelength of light stretches as objects move away from an observer. This is a key piece of evidence for the expanding universe, supporting the theory that galaxies are moving away from us and indicating that the universe has been expanding since its inception. As a result of this expansion and redshift, the temperature of the cosmic microwave background radiation, which is a remnant of the heat from the Big Bang, has cooled to just a few degrees above absolute zero today. This cooling and expansion is a fundamental aspect of cosmology and helps us understand the evolution of the universe over billions of years. Is it possible to eliminate all matter and energy from the universe? If so, what would remain? There would still be empty space, governed by the laws of physics and filled with quantum fields. Dark energy, a mysterious force, accelerates the expansion of the universe. This space would continue to grow, even in the absence of particles or radiation. Inflation played a crucial role in the universe's history. The rapid expansion that occurred before the Big Bang, known as inflation, was significant in shaping our cosmos. Before inflation, there was likely a powerful type of energy in the universe that stretched space at an unimaginable speed. This expansion smoothed out any early irregularities, resulting in the uniform and even universe we observe today. However, inflation raises new questions. Where did it all begin? If inflation occurred indefinitely in certain regions of space, leading to an infinite number of Big Bangs, how does this affect our understanding of the original Big Bang? To address these questions, we need to examine three key concepts: the hot Big Bang, the theory of cosmic inflation, and the notion of an ultimate beginning. The Big Bang and inflation are distinct yet interconnected ideas. In the early 20th century, astronomers such as Edwin Hubble and Vesto Slipher observed that galaxies were moving away from us, which suggested that the universe is expanding. This expansion implies that the universe must have been much smaller and denser in the past, leading to the formulation of the Big Bang theory, a moment when all matter and radiation were compressed into a single point of infinite temperature and density. However, the Big Bang theory could not fully explain certain observations, such as the universe's flatness and uniform temperature. This is where inflation becomes relevant. It is possible that inflation is responsible for the universe's flatness and smoothness. This implies that the Big Bang was not the true beginning. Rather, it represented a transition from the inflationary state to the hot, dense universe we know today. The Big Bang theory, while explaining many aspects of the universe, also faces several challenges, particularly the horizon and flatness problems. The horizon problem arises because regions of the universe that have never interacted with each other exhibit similar temperatures and other properties. This uniformity suggests that these distant areas must have been connected at some point, despite being too far apart to have exchanged information since the Big Bang. Another challenge is the flatness problem, which concerns the apparent perfect balance between the forces of expansion and gravity in the universe, resulting in a flat and stable geometry. This raises the question of how the universe has maintained this delicate equilibrium. Inflation offers a solution by explaining that the rapid expansion of space smoothed out any initial irregularities. Scientists have long pondered why the universe possessed these specific characteristics at its inception. Early theories provided insights into the events of the Big Bang, but more recent concepts, such as inflation theory, clarify why the universe is so uniform and account for the absence of expected particles like magnetic monopoles. The question of what preceded the Big Bang remains an open topic. In 1980, physicist Alan Guth introduced a new framework for addressing these issues through the concept of inflation, an early phase of rapid, continuous expansion. Guth proposed that the universe's energy was not divided into matter and radiation as it is today. Instead, it was part of space itself, driving an extraordinary rate of expansion. Inflation resolves three key problems, starting with the horizon problem. This issue questions why the universe appears to have a consistent temperature and density, given that different regions haven't had time to communicate since the Big Bang. According to inflation, everything was once connected in a compact, dense state before rapidly dispersing, which explains the observed uniformity across the cosmos. The flatness problem arises because the rapid expansion caused by inflation has effectively erased any initial curvature in the universe, resulting in an astonishingly flat appearance. Similarly, the monopole problem is addressed by inflation, as it explains the absence of exotic remnants like magnetic monopoles, which would have formed if the universe had reached extremely high temperatures. Inflation prevented the universe from experiencing such conditions, thereby stopping these particles from being created. In addition to resolving these cosmological issues, inflation also sheds light on how structures in the universe, such as galaxies, formed. During inflation, tiny quantum fluctuations in the fabric of space were magnified to cosmic scales, creating the irregularities that eventually evolved into galaxies, clusters, and stars. Evidence supporting this theory can be found in the cosmic microwave background radiation, which is the afterglow of the Big Bang, as well as in the large-scale structure of the universe. These early fluctuations, although minuscule, were crucial in shaping the universe we observe today. In the 1980s, scientists made precise predictions regarding how these fluctuations would manifest in the CMB, and subsequent observations have largely validated those predictions, reinforcing the inflation theory as a compelling explanation for the universe's origins. However, inflation raises a significant question. If it elucidates events prior to the Big Bang, does this imply that the Big Bang was not the true beginning? The initial model of the Big Bang proposed a singularity, an infinitely dense and hot point from which the universe expanded. Inflation complicates this picture, since it causes space to expand exponentially. Reaching a state of zero size, as suggested by the Big Bang model, would require an infinite amount of time. This makes the concept of the universe originating from a singular point difficult to grasp. Currently, we can only observe evidence from a very brief period, such as the traces left by quantum fluctuations that occurred just before inflation initiated the Big Bang. Eternal inflation adds another layer of complexity to our understanding of the universe. In this scenario, inflation never truly ends. While it ceases in certain regions, such as our own universe, it continues in others, resulting in a multiverse filled with numerous pocket worlds, each having its own Big Bang. This ongoing process obscures any potential records of what might have existed before inflation, making it exceedingly difficult to uncover the origins of our universe. While the concept of eternal inflation is intriguing, it doesn't provide a way to look back in time indefinitely. Research indicates that expanding spacetime cannot revert to an earlier state indefinitely. It must have originated from some initial, possibly singular condition. Thus, while inflation clarifies many aspects of the early universe, it does not necessarily resolve the question of the ultimate source of everything. Other models, such as cyclic or bouncing cosmologies, also struggle with this fundamental issue. These theories propose that the universe undergoes cycles of expansion and contraction, but they do not adequately address the problem of a definitive beginning. When we ponder the concept of nothingness, the question arises, if the universe had a beginning, what was it born from? The notion of absolute nothingness is more complex than it might seem. Even in the emptiest regions of space, quantum fields persist. These fields are active and intercommunicate even in the absence of particles or energy. Thus, the closest thing to nothing is still something, a vacuum filled with quantum potential. The vacuum origin hypothesis posits that the universe could have emerged from a quantum fluctuation in this vacuum state, an idea that has fascinated physicists for years. This theory suggests that the universe began as a perturbation in nothingness, leading to the existence we observe today. Although still speculative, this notion provokes deep reflection on the nature of existence and the essence of nothingness. The universe is more than just the space we observe. It is composed of quantum fields and virtual particles. Quantum field theory posits that energy fields permeate all of space, interacting to form everything from atoms to stars. These fields remain active even at their lowest energy state, known as the vacuum state. Virtual particles, which are transient and spontaneously arise and vanish, continuously draw energy from this vacuum. While these elements are crucial to the universe's structure, they complicate our understanding of nothingness. If space is filled with these dynamic fields, can we truly claim that the universe was ever empty? The accelerating expansion of the universe is driven by dark energy, an enigmatic force. While inflation explains the rapid expansion in the early universe, dark energy accounts for the current acceleration. Even far into the future, after all stars have burned out and matter is widely dispersed, dark energy will sustain the universe's growth. Thus, the universe has never been completely empty and likely never will be, as growth and the associated radiation and quantum fields will persist as long as dark energy exists. The quest to unravel the mysteries of the early universe has occupied scientists for decades, and inflation theory has significantly altered our perspective. However, it also raises new questions. What existed before inflation? What triggered its onset? And why does the universe resist the concept of nothingness? While we may not yet have all the answers, our exploration continues, bringing us closer to understanding the origins of everything we see in the cosmos. And that's it. Thanks for exploring the mysteries of the universe with us. From the Big Bang and inflation to dark energy and quantum fields, we've uncovered some intriguing questions about our cosmos. While answers may still be out of reach, the journey of discovery is just beginning. Don't forget to subscribe to Spaceverse for more cosmic insights and share your thoughts in the comments. Until next time, keep looking up.